Now we shall solve this very interesting problem which is taken from real analysis. Here problem is if f, that is a function, its domain is closed interval 0 1 and its range is the set of real numbers, and also provided f0 equal to f1 equal to 1, value of the function at x equal to 0 and x equal to 1 both are 1 value. Is defined by f(x) equal to 1 over q when x equal to p over q, that is a rational number. Pq obviously belongs to the set of natural number, and GCD, that is greatest common divisor of p and q, is 1. And when x is irrational number, the value of the function is given as 0. Then what is the value of the integral 0 to 1 f(x) dx? We have to find out the definite integral, that is 0 to 1 f(x) dx. This is the problem. The problem is function f, that is function's domain is 0 1, closed interval 0 1, and its range is the set of real numbers, provided f0 equal to f1 equal to 1, and is defined by f(x) equal to 1 over q when x equal to p over q, that is rational number. Pq obviously belongs to the set of natural number, and GCD of Pq is 1. And when x is irrational number, the value of the function is 0. We have to find out the value of the definite integral 0 to 1 f(x) dx. Now let us begin. Here the function is defined as f(x) equal to 1 over q when x equal to p over q. Now let us choose irrational, a positive number irrational such that this irrational greater than 0 and less than 2. Also there exists a natural number k such that k less equal to epsilon by 2 less than k plus 1. There exists a natural number k such that k less equal to epsilon by 2 less than k plus 1. So f(x) equal to 1 by q when x equal to p over q. We can choose the value of the function whose denominator is less than or equal to q. We can choose the number in we can choose the rational number also. We can choose the rational number we can choose the rational number whose denominator denominator whose denominator less equal to k, whose denominator less equal to k. So at these values of x, f(x) greater equal to 1 over k greater than epsilon over 2. This is f(x) greater equal to 1 over k greater than epsilon by 2, because we have chosen the rational number in the closed interval 0 1 whose denominator less equal to k. So the value of the function is 1 over q, where q less equal to k, natural number k. So at these values, functional value, that is f(x) is greater equal to 1 over k, that is epsilon over 2 greater than. So this is the finite set. So this set of rational number whose denominator less equal to k is a finite set. And obviously in this finite set f is continuous, f is not continuous, f is discontinuous, f is discontinuous. Discontinuous because f(x) greater than epsilon by 2. Epsilon is an arbitrary number whose value lies between 0 and 2, whose value is greater than 0 and less than 2. It is arbitrary number, and f is greater than this arbitrary number, so it cannot be continuous in this finite set. So f is discontinuous here, and so f attains finite number of discontinuity. Finite number of discontinuity. And for other values in the interval, for other values of the rational number numbers whose denominator greater equal to k plus 1. The functional value f(x), that is functional value, is less equal to 1 over k plus 1, that is less than epsilon over 2, less than epsilon over 2. So here f(x), so here f(x) is continuous, so here f(x) is continuous, because fx less than, always less than an arbitrary number epsilon over 2. So, fx is continuous. So, we can say fx is continuous here, that is, this is the set of rational number whose denominator greater equal to k plus 1. Also, this set is infinite set. So, now fx f is defined over the closed interval 0 1 and its range is the set of real numbers provided f0 equal to f1 equal to 1. So, we can say f is bounded in 0 1. F is bounded in 0 1 because its highest value is 1 and lowest value also its value is for rational values, for the rational value of x, fx is 1 over q. So, if q tends to 0, q tends to infinity, fx tends to 0. So, lowest value is 0. So, that is lower bound is 0 and upper bound is 1. So, this function is bounded in this interval 0 1, closed interval 0 1, function is bounded. So, function is bounded. Now, for integrability we have to prove the necessary and sufficient condition, which is upper sum minus lower sum of this function is less than an arbitrary number. Now, upper sum minus lower sum, that is summation mr minus mr delta r, where mr is the upper bound in the subinterval del r, in subinterval xr minus 1 xr whose length xr minus 1 equal to del r. mr is the upper bound and also the lower bound is mr. In each subinterval lower bound is mr. mr is the lower bound in the rth subinterval, that is xr minus 1 xr. This is. Now, we can enclose the finite number of point of discontinuity. We can enclose finite number of points of discontinuity by subinterval subinterval x1 minus delta 1 over 2 x1 plus delta 1 over 2 x2 minus delta 2 over 2 x2 plus delta 2 over 2 dot dot xk minus delta k over 2 xk plus delta k over 2 subinterval. And in these subintervals, the difference between upper sum and lower sum, that is, in this subinterval, in this subintervals, upper sum minus lower sum equal to delta r, and also these functions is bounded in the interval 0 1, so it has upper bound and lower bound, fixed upper bound and lower bound. Suppose this fixed upper bound is m and fixed lower bound is small m. Obviously fixed upper bound is 1 and lower bound is 0. So we can write this less equal to m minus m into del r, that is m is the entire upper bound and m is the small m is the entire lower bound, that is m is the fixed upper bound of the function in the entire interval closed interval 0 1 and m is the fixed lower bound of the function in the closed interval 0 1. So obviously mr, each mr minus mr less equal to m minus m, that is this is fixed quantity. We can write this equal to summation del r, and we can each interval, the length of each interval, we can make the length del r of each subinterval less than epsilon over 2 into k m minus m. This is so upper sum minus lower sum, in this finite number of subintervals. So here upper sum minus lower sum less than m minus m del r is that is del r less than epsilon over 2k m minus m. We have made the length of each subinterval del r less than epsilon over 2 into m minus m, 2k, epsilon over 2k into m minus m. So we can write each interval. So here number of interval is k, so k into epsilon over 2k m minus m. Here number of interval is k, so sum of the length of the intervals is less than k into epsilon over 2k into m minus m, which is equal to epsilon over 2. So upper sum minus lower sum less than an arbitrary number epsilon over 2. Now we shall further check the difference between upper sum and lower sum for the rest k plus 1 subintervals where the function has continuity, So we can check for the rest k plus 1 subintervals where the function f is continuous. Where the function f is continuous. Now here upper sum minus lower sum. Here also we can indicate this sum, first sum, that is 1, and we can indicate this sum as second sum 2. This is the difference between upper sum and lower sum in the rest k plus 1 intervals where the function is continuous, and here the difference between upper sum and lower sum for the k intervals, number of intervals is k, this interval the function is discontinuous in these intervals. There are point of discontinuity for the function fx. So here we can indicate this sum, this difference between upper sum and lower sum as UPF and minus LPF 1, and secondly the difference between upper sum and lower sum is indicated as this UPF minus LPF 2 equal to summation MR del R. Also here we can make each length of each subinterval length del R of each subinterval less than epsilon over 2k into m minus m. Now the value of this quantity, there is UPF minus LPF 2 equal to summation MR minus MR del R less equal to also this oscillation less equal to M minus M. Each oscillation, that is the difference between upper bound and lower bound in each sub interval, always less equal to the fixed upper bound and lower bound, difference between the fixed upper bound and lower bound of this function in this interval, closed interval 0 1, that is MR minus MR less equal to M minus M, that is fixed upper bound and lower bound difference between, that is summation M minus M del R. This is constant, so we can write this equal to summation del R, and each del R have made less than epsilon over 2k into M minus M, that is each del R is less than this. So here the number of del R is k plus 1, so total difference, total length of these sub intervals is less than epsilon into number of interval is k plus 1, so k plus 1 over 2k here also we have made the length, each length less than 2 into k plus 1, that is 2 into k plus 1 into M minus M, that is equal to epsilon over 2. So entire difference of upper sum and lower sum is entire difference, that is UPF minus LPF, entire difference of upper sum and lower sum is less than epsilon over 2 plus epsilon over 2, that is epsilon, that is UPF minus LPF is less than 1 epsilon. This is the sufficient condition, necessary and sufficient condition for the function f in this interval, that is 0 1 is integrable. This is for integrability. For integrability of the function f in the closed interval 0 1, this is the necessary and sufficient condition. This necessary and sufficient condition holds, so we can say the function f is integrable in the closed interval 0 1. This is the sufficient condition for integrability. This is the necessary and sufficient condition for f for integrability of the function fx, for integrability of the function f. This is the necessary and sufficient condition for integrability of the function f. So we can say the function is integrable in the closed interval 0 1. So we can say f is integrable in 0 1 because the function satisfies the necessary and sufficient condition for integrability. This is the necessary and sufficient condition of integrability for the function f in the closed interval 0 1. So, as this condition is satisfied, so we can say the function f is integrable there, that is integrable in the closed interval 0 1. Now, lower sum, that is LPF, lower sums is MR del R. Here we have already found the lower bound of the function in the closed interval 0 1, that is MR equal to 0 in 0 1, in closed interval 0 1, MR is 0, that is lower bound is 0. So, MR dr is equal to 0. So, lower sum of the function is 0, lower sum of the function f is 0 in this partition, that is in these sub intervals, for these sub intervals. So, LPF equal to 0. So, infimum supremum LPF is also 0, supremum LPF is also 0, and supremum of LPF, supremum of the lower sum of the function for this partition is 0, which is defined as lower integral fx dx. This is so, as this function is integrable, since f is integrable in 0 1, we can write integration 0 to 1 fx dx equal to 0 up lower integral equal to upper integral fx dx. Now, lower integral fx dx equal to 0 is already got as 0, lower integral is 0. So, entire integral, value of the entire integral, that is 0 to 1, value of the entire integral fx dx equal to this is the value of this integral. We have found out the value of this integral 0 to 1 fx dx, whose value is 0. The value of the definite integral 0 to 1 fx dx is 0 is got. Thus, we have found out the value of this definite integral in the closed interval 0 1 of the function fx.